Alright, quick question. What's the value of this sum? 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared and so on. Seems chill, right? But this was an actual unsolved problem for nearly 100 years until Euler pulled up like pi squared over 6. Pi squared? Bro, this isn't even a circle. Wait. Unless you're 3 blue 1 brown, then yeah. Okay, let me show you something familiar. Take this random quadratic. Y equals x squared minus 3x plus 2. We set y equals 0 and solve it like normal humans do. X equals 1 and x equals 2 are the roots of this equation. Now here's the cool part. We can rewrite this using its roots. Y equal to x minus 1 times x minus 2. Store this in your brain. This is going to be our launch pad into sin x territory. Now let's bring in the big boy sin x. Where does it become 0? X equals 0 plus or minus pi plus or minus 2 pi, and yeah, multiples of pi. So we try this monster. X times x minus pi times x plus pi times x minus 2 pi times x plus 2 pi. We can rewrite this as x times x squared minus pi squared times x squared minus 4 pi squared times x squared minus 9 pi squared and so on. Here's how that looks on the graph. You can see it's touching 0 at pi, 2 pi, 3 pi, just like sin x. The function just blows up between the roots. It gets taller and wilder with each new term. It's like the function is on too much caffeine. So how do we fix it? Sin x equals x times 1 minus x over pi times 1 plus x over pi times 1 minus x over 2 pi and so on. You can rewrite this as x times 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared and so on. Now look at this graph. As we increase the number of terms, it actually starts looking like sin x. No more chaos. It still hits all the right zeros but stays controlled in between, like a well-behaved version of the earlier one. Let's now divide both sides by x. Why? So the left side becomes easier to compare later. We're basically simplifying the playground before the real fight. And also, I hope you noticed the n squared in the denominator. Now the other side of the story, the Taylor expansion of sin x. Divide both sides by x again. That minus x squared over 6 term, keep your eye on it. It's about to do something spicy. Let's go back to the project side and expand it to just the first few terms, nothing crazy. Multiply it out and the x squared terms turns out into this beautiful thing. Minus 1 upon pi squared times 1 over 1 plus 1 over 4 plus 1 over 9 plus times x squared. Well, we really do not care about the other terms, x to the 4th or x to the 6th. From the Taylor side, we had minus 1 over 6. From the Euler product side, we got minus 1 upon pi squared times the summation. If these two ways of writing sin x upon x are actually the same, then their x squared coefficients have to be equal. So now we cancel the negatives and rearrange. There we get pi squared upon 6. And just like that, Euler turned a boring looking sum into a pi squared masterpiece using pure algebra and trig. Euler did the math. You just gotta do your part. Like, sub, drop a comment. It's way easier than solving the Basel problem. I promise. See ya.